and welcome to the first video I'm going to be doing in a series for the machines test for Science Olympiad. This series will mostly gained towards people who have already took Regents Physics or AP Physics 1, so if you haven't took those, you might want to reconsider doing this event. However, in this video, it should be pretty light on the math and the physics, and we're going to talk about actual mechanical advantage, ideal mechanical advantage, and efficiency. So, very important topics for you to know, and we could start learning about them now. What mechanical advantage is, by its most basic definition, is the ratio of the output force, the force you get out of a machine, divided by the force you put into the machine. So let's say, for instance, we have a certain machine, let's say a lever, that produces 100 newtons of force, but it takes 20 newtons on the input. We call this number here the output force, and this number here the input force. So if we divide them, we get 5. But if you notice, the units newtons cancel. So that's very important. The mechanical advantage is a unitless quantity. It's not like newtons, meters, seconds. There is no units. It's just 5. The actual mechanical advantage is 5. Now, how this differs from ideal mechanical advantage. Ideal mechanical advantage assumes a world with no friction, no air resistance, no loss due to heat, or any of the other things we don't usually consider in physics. Most of the times, we will be working with ideal mechanical advantage if we're finding it. However, if it's given to us, it might be the actual mechanical advantage. So, the formula for ideal mechanical advantage is not F out over Fn. It's D in over D out, which might be a little confusing because the F out over Fn, and this time it's the input over the output. What this means is distance and force have opposite relationships. If distance increases, then force will decrease. This has to be true by energy conservation. No machine could both increase the force and increase the distance. So for example here, let's say IMA is the same as AMA. You might produce 5 times the force, but only move 1/5 the distance. Before we move on, let's just do one really simple example of this. Say we have a machine with an AMA of 10, and we put in 25 newtons of force. How much force does the machine exert? So to solve this, we know that AMA equals F out over F in. Now, we know Fn and we know the AMA. Now, it's simply a matter of isolating for F out and then solving the equation. So it's AMA, oops, that is the wrong number, is 10, and the input force is 25 newtons. So now we just call this F, and we can multiply both sides by 25. And for this, we get 250 newtons. So this is a real... One more thing I want to go over is the concept of efficiency of a machine. The efficiency, which we use Greek letter nu to represent, is simply the ratio of the AMA to IMA. Now, it measures essentially how much of the energy that we put into the machine comes out of the machine. And it ranges from 0 to 1. In reality, we can never build a machine with the exact same AMA as IMA. The AMA will always be smaller than the IMA. This makes sense because one's ideal and one's actual where you lose stuff, but you can't really gain efficiency. So it's always between 0 and 1. So for instance, if we have a lever and it loses a lot of its energy to, let's say, friction, then that would be a very inefficient lever. Now, sometimes they might give you the D in, D out, F in, and expect you to find the efficiency. What we could prove is if AMA, as we said before, is FO, which is out, over FI, which is in, and IMA is DO over D in. Now, if we plug these into the equation, we get F out times D out over F in times D in. I'll use the multiplication sign. So, if you ever took Regents Physics or maybe AP Physics, you've definitely seen force times distance. What a force times distance is the energy. So this is the same thing as work or energy out over work or energy in. This is why we could also write as this. AMA over IMA is the work out over work in. This doesn't mean that the AMA is the work or the IMA is the work. It just means it's the same thing. So if we put 80 joules into a machine, 80 joules is a measure of energy, which is the same thing as work. And on 60 joules comes out, this would have an efficiency of 60 over 80, which is 0.75. This would be the efficiency of this machine. Here we have the final example of this video. It kind of summarizes everything we learned. And it says, we apply a distance of 5 meters and 10 newtons to machine that outputs a force of 4 newtons and 6 meters of distance. Calculate the efficiency. Now, there's actually two ways to do this. We could use the AMA or IMA formula if you want to pause the video and try that. Or you could do what I believe the simpler option, which is the work out over work in. Now, you do have to know that the formula for work is force times distance. That's important. So you probably should take physics before you really venture into machines, because it builds off a lot of the concepts in physics, like this. Work equals force times distance. So what is the formula is work out over work in. The force out is 4 newtons. And the distance out is 6 meters. 4 times 6. But we put in 10 newtons and 5 meters. So now we can see here, it doesn't matter if the distance gets larger or the force gets smaller or larger, because if one goes up, the other must go down. So that's how we could have like small input force create hundreds of thousands of newtons of output force, because it only travels a small distance, which maintains that the work is the same. So if we solve this, we get 24 joules over 50 joules. And we plug this into our calculator, we get 0.52. Once again, the efficiency is not a unit quantity. I mean, there's no units behind it, so it's not like newtons or meters. We just 0.52 or 52%. In the next video, I'll be talking about some simple machines that you'll have to know, like levers, pulleys, gears. And if you want to stay in tune for that, make sure you subscribe and like the video. And I'll see you